Hello. Oh, okay. Hello. Well, okay. Hello, everybody. I'm just gonna say hello, everybody. I will admit that some people have been in the waiting room for a very long time and have texted me. I'm just saying, but okay. I will, but I'm not gonna get okay. We've got a lot to do. Oh my God. Oh my God. And she's even showing video. I mean, some people whose name, oh my God, she's even showing video. Whoa. Well, oh my God. Wow. And uh, oh my God. Okay. This is, I, I can't even, I'm so, I don't even know what to say, but, yes, I would, but not right now. I know you'd be on time for your job, that's for sure. Okay, wait, okay. No, I'm very, oh, and hello, okay, yes, hello, Newell. It's good. Okay, wait, I'm gonna do okay. Hi, John. Hi, Maisha. Hi, oh, get wrecked. Good heavens. Wait, okay. Hi, John and Maisha. I'm just saying that. Now, hello, Eric. How lovely to see you, Eric. Um, Hello, May. How lovely to see you, May. Hi, Lizzie. Good to see you, Lizzie. I'm going to skip that. 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 Hello, Elizabeth with an S. How lovely to see you. Hi, Newell. How lovely to see you. I'm totally not. Okay, I'm stepping back from the madness. Well, sort of. Wait, someone else is here. I'm sorry. Hold on a second. Oh, and that's Leia. Okay. But I also do want to say, okay, and we do have to get to something today. And whoa, oh my God, it's getting so wow. Okay. But I do want to wow. Okay. Good afternoon. I'm back. Oh, good. so okay. Good afternoon, Alea. I'm starting to get just when I got your name right. Then there's someone in the other class whose name is really similar but pronounces it differently, and it's throwing me back. It's all very complicated. But hello, and I don't know if OG in this context means original gangster or means oh God, he's what did it mean? It meant yeah. Okay. Right. Okay. Yes, you are definitely and you are the original. Yes, you are totally original. Right. But the other, okay, anyway, I'm going to shut up. We're going to do physics because I clearly should not be trying to do anything but physics. You do have lab again this week. Just want to say lab is back in action this week. And I believe that what we're going to do today should actually help a bit with lab. But all right, I'm going to go. Okay, let's, oh, sorry, hold on. Okay. What today, we are going to finish what we were doing last Wednesday. I'm going to step back a little bit and remind you / review what we were concluding at the end of last Wednesday, because it actually is super big and super important. Technically, again, just to remind you, technically what we're getting is an answer to question 9 of homework 1. We never got a number for that. I mean, technically question 9 of homework 1 is asking for a number. So we will get that number today. But I really want to emphasize to all of you, I know the fact that it's taken us like a month to get through all these questions of homework 1 is again for a reason. It's because ultimately homework 1 is ultimately driving at a very big, important conclusion that does relate to many labs, that relates to so many topics and relates to PChem. The topic is simple harmonic oscillation. So yes, we're going to get a numerical answer to question 1 and finally put homework. I'm sorry. Yes, we're going to get a numerical answer to question 9 and finally put homework 1 really to bed. But I cannot emphasize enough that the important thing about question 9 and the important thing about the whole sheet is not any one particular numerical answer, but it is the ultimate knowledge that we're trying to gain about the differential equation that governs simple harmonic oscillation. Ultimately, the solution to that differential equation has this term called omega in it, like this thing right here on the board here. Omega is the lowercase Greek letter that looks like a W, but it's actually the lowercase Greek letter omega. It ultimately stands for something called angular frequency. I haven't said that yet in lecture, but you may have seen it on the web or you may have heard it in lab or something. Ultimately, omega stands for something called angular frequency, which is ultimately the thing I want to try to make as concrete as possible by the end of today. Ultimately, it relates to standard frequency and relates to period, which are different equivalent ways of measuring the rate at which some kind of regular, patterned, predictable harmonic oscillation occurs. Okay, so in other words, angular frequency, standard frequency, and period are three related, ultimately equivalent, but nonetheless distinct ways of tracking the rate of motion of some harmonic oscillation, some back and forth cyclical motion. Ultimately, omega is our description of how rapidly or how quickly some harmonic oscillator is cycling back and forth, back and forth, back and forth. That's ultimately the point. That's ultimately the point I want to get to today. In so many words, that's what it sort of says on the front page here, but the front page may or may not make sense to you. It's what I want to ultimately get to today. But the way we get there, the way we sort of discover or fall on top of this omega is by solving the differential equation that governs simple harmonic oscillation. That is what question 9 is really about. That's what homework 1 is really about. So bear with, or so forgive, it's so important and so big. And yes, certainly involves us in calculus, like for good or for bad, it brings us back to calculus. So what I'm going to do right now, if you look at the page, I'm going to back up a little bit to sort of, you might recall last Wednesday, we were trying to test and verify a possible solution to a differential equation. And we were testing it and verifying it by taking derivatives. I turned it to you guys. I gave you this cosine function. I asked you to take 2 derivatives, and it involved some thought on many people's part. Like it was a little bit of a walk down calculus memory lane for many people. Like for some people, it was a totally like awful experience. Maybe like for some people, like they didn't remember at first, but maybe once they were reminded or refreshed, then they did remember. Others of you might still want to contact me in private. Like, and honestly, you might still want to direct chat or text me and say, I'm still not comfortable with this calculus thing. Can you refresh me? And I'll try to accommodate that. But what I'm going to do right now is back up just a little bit. Instead of making you do the calculus again, I want to back up to like why the calculus came up, why those derivatives came up, what they were supposed to be doing. We got so involved in taking the derivatives, it's possible to me that not everybody knows exactly why we were doing that or what it accomplished. So here we are on this page here. Let me remind you, we're finishing question 9 of homework 1. The question was, given some mass on a Hooke's law spring on a stiff spring of stiffness K, the question of homework 9 was, at 1 second into the motion, where do we find the mass? Like, so at t equals 1, what's x, right? That was the question. And we will technically answer that. But again, I'm here to say really, the question really was, given some f equals negative kx situation, given some general mass that's governed by a general restoring, by a linear restoring force, what can we say about the equation of motion? What would be our general xt relation for a system that is generally governed by f equals negative kx, right? That's really, in larger terms, the question posed by question 9, right? So that's a bit. So what we did was we said, okay, and obviously, again, stop me if you want me to go back, back to any slide or whatever. excuse me. So we did a little bit of quick algebra. We said, okay, f equals negative kx is the main condition here. And of course, we're physicists, so Newton's second law of motion is always true, net F equals ma. So we just like algebraically put the two together. And we said, oh, okay, the situation we really have here is a equals negative k over mx. And a, acceleration, instantaneous acceleration, is the second derivative of x with respect to t, right? So what we found, so again, this is technically what I'm doing right now is like technically review of last Wednesday, but hopefully it's clarifying. What we found was d2x over dt squared equals negative k over mx. Like we landed on this differential equation. We landed like from the physics, not because like we want to do particular math, but just the physics led us to this math situation where we have this dependent variable x stands for position. And we find that the instantaneous rate of change of x with respect to time, right? We found that the time derivative of the time derivative of x, in other words, the second time derivative of x, is equal to x itself times a constant times a negative sign, right? I mean, I'm sort of reading it backwards, but that's what it says. It's like, in other words, Hooke's law, once we write it in sort of general mathematical terms, like Hooke's law, when you first see it, it says force equals negative kx. But since force is always directly proportional to acceleration, what we're really saying in the end is, oh, the rate of change of position with respect to time, like the rate at which position changes in time twice is directly proportional to position itself, right? That's what we're saying. We're saying the rate of change of position with respect to time is equal to negative times a constant times position itself. Times a constant means directly proportional to. And that negative sign means, directly proportional to, but always in the opposite direction, always restoring. If position is in the on the right-hand side of equilibrium, then the rate of change, the restoration will try bringing it to the left to equilibrium. If the thing is on the left of equilibrium, then it's going to be pulled to the right. It's always being pulled back toward equilibrium. So what we found was that Hooke's law, once it's written in general, is this second order differential equation. And then we were trying to solve it, right? Again, I'm reviewing here, but I think this is new to many of us. So we are trying to solve it. And I got to be clear about that again. Like this thing is an equation, but it's not this thing in the middle of the page, this black d2x dt squared equals negative k over mx. It certainly is an equation. It certainly contains a lot of really important information in it, but it's not an answer to our troubles. It's the question. Like, what we're looking for is x as a function of t. We're looking for some rule where you plug in a value for t on the right side, and then a bunch of things happen to it, and it spits out an x on the left-hand side. That's not what this is. This is something that tells us about the rate of change of x with respect to t, right? So, and that's the way, so differential equations are super important. They come up all the time in physics and math, whatever, but they need to be solved. They are not a solution. They need to be solved. It is much like Jeopardy in a way, where what we have here, like, oh, someone said, sorry, whoa, hello, sorry. Okay, it's much like Jeopardy in that, in a way, we're given an answer and we have to now construct the question. What do I mean? Like, we have to sort of think backwards, and that's why I spend so much time on this, really, and why, like, I'm going to keep backing up, like, I'm going to keep going one step backwards and two step forwards to do it, because it is a kind of reverse engineering type thinking. It is backwards thinking. What do I mean? I mean that differential equation says that there is some function out there for which it is the case that when that function is differentiated twice, it gives back itself times a constant times a negative. In other words, that equation is not saying take your function and differentiate it twice. It's saying you got to find a function which, when it's differentiated twice, produces a certain result. Okay, so we're looking for that function x of t for which it is the case that when it is differentiated twice, it produces x times k over m times the negative sign. Now, I keep saying it in that funny way because before I go any further, just please note, k is some number. Why don't I just write it as a number? Well, because it's a different number for every different spring, right? It's not a variable. It's a constant because it will stay constant for a given spring. K, I'm talking about. K will stay constant as the mass goes back and forth, as x changes and as t change for a given oscillating spring. K won't change for that. It is literally a constant number, but I just leave it as K because I don't know what the number is. This is really what I mean by a constant. It's constant, but I don't know what it is, and it could be anything depending on the spring. Same thing as M, right? K and M for a given spring, for a given system, are each constants. Now, why am I making a big deal of this? Because a constant divided by a constant is still just a constant. Like a number that I haven't named, but is a number, divided by some other number is just a number. Okay, so what I want to emphasize before I go any further, what I want you to see is that business inside the parentheses, it is K over M, but it's just some freaking number that I don't know. Like in the case of our example here, homework 1, it happens to be 200 divided by 0.3. I think that's like 625 or something like that, I think. If I'm wrong, I'm wrong. I don't really care what the number is. The point is, it's just some number. So that whole parentheses is some constant, right? So really, we're just saying the second derivative is directly proportional to the variable itself, but then times -1, like times a negative sign. That means this whole thing is restoring always. All right, so we've got to find an x. We're looking, or we're looking for an x that meets that condition. Think of the differential equation as a condition. Think of our solution that we're trying to find as a function that meets that condition. To say we've solved the differential equation means we've found an x that meets the condition of the differential equation. Okay, so what did we do? So I'm about to turn the page. What we did, we conjectured, we thought through using our best experience from the lab and from mathematical background. We came up with a guess that we thought was pretty good, but it was just a guess. It was a very educated guess, but it was just a guess. We came up with a guess for what type of function x should be. And any details we thought we knew, we filled into the best of our ability. That didn't make it right. We just came up with a guess for the function x. And then we said, okay, the whole point is that if this x is right, then when we take a derivative of it with respect to time, and we take a derivative again, when we take two derivatives of it, when we get its second derivative with respect to time, it should end up equaling something like -k over m over x. And if it does, then we're right. And if it doesn't, then we're wrong. So that's why we were taking derivatives last Wednesday. We were taking derivatives of our conjectured x function to see if it worked out. So this is what we did. So next page. So we conjectured x equals x naught cosine omega t. Now, let me, even before I go any further. Okay, now, so we made this guess, x equals x naught cosine omega t. Now, x naught, we know what that is. X naught means the position when t equals 0. But the omega, remember, and please bear with, again, please stay with me here. We introduced this omega like Wednesday. You might have seen it on the web and you might have seen it in the lab, but I never said anything about omega before. We're introducing it now. We're introducing it because as part of our guess. Omega is that Greek letter could have been any letter that stands for some number. We don't know what the number is, but we believe there's got to be some number multiplied by the t before we even take a cosine of it, for the simple reason that you can't take the cosine of a second. We just believe there's got to be some number measured in radians per second to cancel out the seconds that we find in t and leave us with radians. That's all we know. Okay, so again, I know it can be very intimidating and it can throw people off when they see that omega, and especially because you're going to see that omega a lot. So what becomes hard for people is like after they start seeing it a lot, they think they've always been seeing it, and they can't sort of find in their notes when I ever explained what omega was, or like that's because we didn't start with a definition of omega. We don't have a definition yet. It's just a placeholder. It's just a name for an unknown number that we believe must go there just to make the units work out. Okay, so there's two things I know about omega at this stage when I'm just building this conjecture. One is that it's has units of radians per second, okay, because that's why it's there, to make those units work. And two, that whatever number it is, whatever this number means, it is a number, i.e. it's a constant, okay? Just like x naught is a constant, right? That much so we built this guess. We said, all right, the basic shape of our function is a cosine shape, and the details of the shape are living in these two constants here, one of which we already know a lot about, x naught, the other which we don't know a lot about yet, but it's got to be there. So we have a guess that has a certain shape and has certain details. Not all the details are worked out yet. It's just a guess. So then we said, okay, let's just work with that guess and see if it's right or not. And how do we see if it's right? We take derivatives of it, right? So again, this is what you guys did for me on Wednesday, but it took just long enough, and I wasn't bothered. I was very happy. It made me feel like, okay, this is time well spent. But because it took a while for people to take these derivatives, what I'm saying is then fine. We got involved in the trees on Wednesday. Let's step out of the trees now and look at the forest of like why that was even happening. We took the first derivative dx dt. We took the first derivative dx dt, and we realized, okay, it's a trigonometric derivative. So the derivative of cosine is negative sine. And we realized that it's really the trigonometric derivative of not just t, but of omega t. It's really the function of a function. So we had to deploy chain rule as well, right? It's not a joke derivative. It's a trigonometric derivative with chain rule involved. So we so to speak, pulled an omega out of the parentheses. Like we got negative x naught sine omega t, and then multiply the whole thing by omega. And then I'm just saying multiplication is commutative. So I just like wrote the omega in the front, just combined it with the other constants, because that's what physicists do. They like to gather the constants and keep them together as a package of constants, and like to keep the variables clear and separate. We're really trying to keep constant track here. Continual track of what is a dependent variable, what is an independent variable, what is a constant, what is a universal constant, what is a parameter. That's the kind of track that we're trying to keep. Okay, so the first derivative is of x with respect to t, dx dt equals negative x naught omega sine of omega t. And why the negative sign? Because remember, the derivative of cosine is negative sine, right? Like that's kind of again, that too on the side I can explain to people if you want, but it's also always true if you want to remember it. Then we took another derivative. We took the second derivative. Why? Because we're trying to test for d2x dt squared. Like we're trying to test for our second order differential equation. So we took another derivative. We did d2x dt squared. And what happened there? Well, first of all, we have a bunch of constants. They always stay there for the derivative, right? Like we have negative x naught. We could even, well, yeah, we have negative x naught omega, like sitting there at the front. They just get carried along for the derivative ride. But we now have sine. Well, the derivative of sine is cosine. So sine turned to cosine. And then it was function of a function again. It was. So we had to do that chain rule thing again. When I say again, I mean just like we did with the first derivative. We still have, we have sine of omega t. So omega comes out again. There was already an omega in the front from the first derivative. Now there's a second omega in the front because it's a second derivative. So we get negative x naught omega squared cosine omega t. I'm in the second to last line of the page right now talking about. Now, please note this. Please note this. Like the omega came out twice because we did chain rule twice. But notice the negative sign did not unnegative itself. Like this sometimes confuses people. Like, please remember, the derivative of cosine is negative sine, but the derivative of sine is just cosine. Or put another way, excuse me, the derivative of negative sine is just negative cosine. We're not doing a double negative here. We did do a double omega because the omega was sitting there the whole time, but we're not doing a double negative. It's not a negative. It's not negative times negative equals a positive. One negative came out because we did the derivative of cosine and got negative sine, but then we did the derivative of negative sine, and that is just still negative cosine, if that makes sense, right? So in other words, a negative sign got introduced somewhere along the way with these derivatives, and it stayed there. It never went away. And that's not an accident, and that is important. So we get that the second derivative of x with respect to t is negative x naught omega squared cosine omega t. That's the second to last line on the page here. And then I just say, okay, fine. Like, what is that? I don't know. It doesn't really tell me anything. Fascinating. Thank you. I just did two derivatives. But then I say, but you know what? Like, multiplication is commutative. Like, order doesn't matter. So I can clean this up a little bit. I can just, all I did on the very last line is I just rearranged. And I said, okay, x naught times omega squared. That's the same thing as omega squared times x naught. Right, so on the very last line, I just a different way of writing that second derivative. The second derivative, d2x dt squared equals negative omega squared x naught cosine omega t. Okay, that would not be a big deal. That would just be the end of the discussion, except as you see from the red here, I'm circling x naught cosine omega t, because what is that? That is our original conjecture for x, right? Like, you see on the last line, x naught cosine omega t. Look at the top of the page now, equals x according to our conjecture. That's the very x that we're testing. Have we proven anything yet? Not quite, but we apparently are saying, we're saying if we equate x with x naught cosine omega t, then when we take two derivatives with respect to time of that x, we get back x itself times omega squared times a negative sign. But we get back the original function times some stuff if we differentiate it twice. Notice, not if we differentiate it once. If we differentiate it once, we get sine, not cosine. Like, that's fascinating, but that's not a conclusion. If we differentiate it a second time, we get back that original cosine. Not only that, we get a negative sign. And isn't that what we wanted originally? Like, so next page. So evidently, what I'm saying here is if x equals x naught omega, if x equals x naught cosine omega t, then the second time derivative of x equals negative times this constant called omega squared times x itself. And remember, that's what we wanted in the first place. We wanted the second time derivative of x to equal negative times some constant times x. Like, if you're thinking like a mathematician now, I mean, if you're thinking in general terms, like, in other words, don't get too bogged down in whether something is an x or a t or a y or a k or an m or an omega or a number. Just think in larger terms, whether something is a variable, whether something is an independent variable, or whether something is a dependent variable, or whether something is a constant. If you think in those terms, like, oh, variable, constant, variable, then you see our original differential equation said second time derivative of x has to equal negative times some constant times x. And what we just got when we played with this like weird omega thing, we got second time derivative of x equals negative times some constant times x. What's the difference between these two equations? Simply that in one case, we're calling that constant k over m, And in the other case, we're calling it omega squared, but those are just names. Like a constant divided by a constant, a number that we don't know divided by some other number that we don't know is a number that we don't know. Similarly, a number that we don't know squared, multiplied by itself, multiplied by that very same number that we don't know, is just a freaking number that we don't know. I don't know what K over M is. I don't know what omega squared is, but I know this. If that's just two different names for the same thing, then I've solved my differential equation. So what I wrote on the right here is like, no, omega is a constant. So omega squared is a constant, just like K and M are constants. Okay. So as long as, so what I'm saying is that cosine expression was a good idea. It was good to conjecture that our position function for an oscillator is a cosine function. Let me even, before I turn the page, let me say that a different way. Like, as scientists, we conjectured that the equation of motion should be a cosine because as scientists, we pictured what we would see in the lab if we took a bunch of data and then made a scatter plot. We would picture something going like on a coordinate plane. If horizontal axis were time and the vertical axis were position, we would see a cosine function, I think. So we all thought, let's try a cosine function. That was like based on physical experience. Now I'm saying mathematically, actually, that makes total sense. We want a function which, when we differentiate it twice, we get back itself times a negative sign. Hello, that's cosine. Cosine differentiated once is negative sine. Differentiated again, like a twice, that's negative cosine. Is that the only function in the world that does that? No, not necessarily. I'm not saying that. Like, if you're following me at all, and if you're thinking, well, wait, doesn't sine do that too? Then like, yay, you. And by the way, if you even were thinking that and want to put in the private chat, like or any chat, get like lots of points. If you're thinking to yourself, hold on, why does he keep saying cosine? Like, wouldn't this work for sine too? Then you are definitely following along. If you're thinking that at all, you're right. Almost all the math I'm saying here would also work for sine. I'm not saying this is the only function in the world that works. I'm saying I like this one the best because sine starts at 0, 0, right? With sine, when t equals 0, x would equal 0. And that physically doesn't make a lot of sense to me. If we just put our mass at the equilibrium position when the experiment started, it would never go anywhere. There would be no experiment. So physically, I think cosine is more quickly, conveniently a descriptor of what we're talking about here as scientists. But if you want to know whether you're following the math, then you're thinking, well, I feel like everything he's saying mathematically would be true of sine also. You're darn tootin'. That's good. There are other functions as well. But so I'm not saying we found the only solution here, but I'm saying we found a solution. Cosine is a good description of anything that follows Hooke's law, because anything that follows Hooke's law has accelerates at a rate that is proportional to its position. Okay, so we're just about there in terms of an answer for question 9. But I'm saying ultimately, I'm saying someone's here. Okay, yeah, I'm saying our original conjecture, remember, our equation was d2x dt squared equals negative k over mx. Our conjecture was x equals x naught cosine omega t. I'm saying that conjecture has just been verified. Our function that we're trying, x naught cosine omega t, works, is right, it solves, is a solution, as long as this omega thing that we don't even know what it is, that we just said sort of had to be there and had to be measured in radians per second. What we're saying is, oh yeah, as long as that squared is k over m, as long as omega is just omega is just another name for the square root of k over m, or as long as omega squared is just another name for k over m, then we're good. So in a way, what I'm saying, you could say it one of two ways. You could say, okay, so you just did solve the differential equation as long as you meet a certain requirement, as long as you restrict yourself to saying that by omega, what you meant the whole time, even if you didn't know it, was square root of k over m. That is one way you could say what I'm saying. Another way you could say what I'm saying is, oh, we just accomplished two things in one. We just got two pieces of knowledge for the price of one. We solved our differential equation, That is, we got an equation of motion for our oscillator, and we even found out something extra about one of the arbitrary constants, the omega. We not only solved with a cosine function, but we found that that placeholder omega, we found what it is. What it is the square root of the spring stiffness over the mass. Like, that's what we're saying. So how does this, any of this become concrete or applicable? Like, what does this do? So on a practical level, if we're just trying to get a freaking answer to question 9, finally, that much we certainly can do. Yeah, so here we go, solving for question 9. So if d2x over dt squared equals negative k over mx, then what we're saying is, okay, we're saying x equals x naught cosine omega t, for which omega is square root of k over m. In other words, if you want something to plug into to get an answer for question 9, we finally have something. Let's plug it. Like, K we know is 200 newtons per meter, M we know is 0.3 kilograms, T is 1, in this case, 1 second, X naught is 0.15 meters, or in other words, 15 centimeters. So let's just go ahead and plug those numbers in to the cosine function and spit out X. Whatever X is spit out by our calculator will be the answer. One warning though, the reason I'm like sort of pausing on this, please note, we arranged this whole thing so that omega is measured in radians per second. Everything I'm saying here assumes radians, not as opposed to degrees. So if you're going to put these numbers into your calculator and press cosine, which is what I'm saying to do, make sure your calculator is in radian mode. This all assumes radian. So if you go ahead and put these numbers into your calculator, you'll get approximately 0.118 meters as the answer to question 9. Finally, like months later, here's the answer to question 9 is approximately 0.118 meters. A couple of quick things to say about that. One thing, I say approximate, not because I'm guessing or because I'm being loose. Oh, sorry, absolutely. And thank you for asking. Oh, that's totally participation. And she went public thing. Yes, absolutely. Sorry. Thank you, Lizzie. So I'll just talk for a second. I just want, when I say that the answer is approximately yada, 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 I'm only saying approximately because we're taking a square root, and the answer to the square root, the digits will go on forever without repeat. So I'm chopping off, at 3 significant digits or something. So I'm saying approximate because we're chopping off digits, but not because we're like pretending or so. Okay, cool. Thank you. Thank you. Awesome. Yeah. Okay. So the answer is approximate. So again, for everybody, this is the, and by the way, can you still turn in this homework? Like, yes, you can. Do I still owe it to you? Yes, I do. Both are true. And does this mean soon we're finally going to get some new homework? Yeah, it does. I'd like to get you yours back first to not be cruel. But yeah, we're the fun times are over. We're going to have to start having new homework soon. Anyway, the answer is approximately 0.118 meters. Can I also point out, now that we've done all this work, that, there's nothing special about that number, like I keep saying, but it is a reasonable number. It's reasonable in that it's between 0 and 0.15. Remember, the whole mass in this particular case of homework 1, the whole mass started at position 0.15 meters, and then it comes all the way into the equilibrium, which is 0, and then it goes to negative 0.15 on the other side. So at 1 second, I hope that I would get an answer that's somewhere in between 0 and 0.15. If I got something greater than 0.15, I've definitely done something wrong, but I didn't, so that's good. Doesn't prove that I did it right, but at least I didn't obviously do it wrong. Excuse me. Okay. Pause for a second. I'm just looking. So finally, just in terms of concreteness or like academics, like that finally sort of wraps up homework 1, thank goodness. But again, I'm saying we've been spending all this time for a reason. there's really a lot going on. Like there's really a lot of chapters and a lot of lessons I'm trying to unearth with each of these different questions. So really, so the answer that we just got, 0.118, is for, or let me say even better. The relationship that we just got, omega equals square root of k over m, like, to be honest, you can memorize that if you want. It does come up a lot and you'll find it on the web a lot, but you got to be very careful. It's not really the major takeaway. What that is what omega equals. I mean, the omega that's in the cosine function. That's what the omega is if there really is a specific m and a specific k. If we specifically have some block of mass on a coil of metal and it's oscillating harmonically back and forth, then indeed omega equals square root of k over m. But the larger thing that I'm trying to say about all of this, which I'm going to say in the next page, is that what we're really talking about here in general is simple harmonic oscillation. And in fact, a lot of times I write SHO, like I think I wrote it in one of the pages of these notes, and I write it a lot of times in like the video names stuff. SHO, I apologize if this wasn't clear. SHO stands for simple harmonic oscillation. That's the broader topic that we're talking about here. That's the kind of system that this is. And a simple harmonic oscillator doesn't have to be a block of mass on a coil of metal. A simple harmonic oscillator is anything that behaves like a block of mass on a coil of metal, i.e., anything that ultimately oscillates at a regular rate because it is being perpetually subjected to something like a Hooke's law restoring force, or more specifically, a linear restoring force, or even more specifically, this. Like, so what I'm saying is we just solved the specific harmonic oscillator, which is a mass on a specific spring. But we want to generalize this. This is our real purpose, is to understand simple harmonic oscillation in general. So let's be general and change. Now this sometimes, oh, that's funny. I thought I, hold on a second. I thought I, okay. Let's switch from X to Z. And I don't mean the Z axis. Frankly, maybe I should switch to the letter Q or something. I'm switching on purpose now to the letter Z. And whenever you see Z from now on in this context of this class, when I say Z from now on, I'm specifically mean any generalized dependent variable, any conceivable, measurable dependent variable that you can think of. Like, in other words, X specifically meant how far the mass was from some literal position on a meter stick, like known as the equilibrium position. So X literally stood for like where you were on a meter stick. But let's broaden our thoughts. Like an oscillator doesn't have to be a mass going back and forth on a spring. It could be, as I think you saw in the lab, or at least discussed in the lab, an oscillator could be a pendulum going back and forth on a string, for which the dependent variable there wouldn't be linear position, it would be angular position, like theta, right? Or what I want to say now is that's another example of there's all kinds of examples of harmonic oscillators in nature and in technology. From now on, I want to say a harmonic oscillator, as it says down there, SHO in blue, a harmonic oscillator is any measurable dependent variable for which the second time derivative of that dependent variable is directly proportional to that dependent variable, but with a negative sign. I'm saying, picture anything you want. Picture, for example, temperature, which actually is the next homework is usually about. Just as an example, picture that you've got some system. Maybe it's like a gas, or maybe it's a liquid in a beaker in the lab, or maybe it's like a bunch, it's like a weather system. It's like a bunch of clouds up in the sky. Picture some system, and you're measuring the temperature of that system every second or every minute or every hour or whatever, right? So you're taking temperature readings in time throughout some long period of time for that system. So in other words, imagine that time is still our independent variable, which it will be for any oscillator, for all these things. We're still in physics here. So imagine that we keep time as the independent variable, but imagine that you're measuring temperature as the dependent variable. So we're going to call it for the moment Z, like Z just stands for that temperature reading that you're taking. If you have any reason to believe, or if you have good reason to believe that the instantaneous rate of change of the rate of change with respect to time of the temperature is directly proportional to temperature itself, i.e., but times a negative sign, if you have reason to believe that, then the temperature is oscillating harmonically. Let me say that a better way or a different way. I'm saying if you're measuring the temperature every moment and you notice that, like, you build up a graph where you somehow come to the conclusion that in effect the acceleration of the temperature, if you know what I mean, like not the velocity of the temperature, not how many degrees you're gaining per second, but how many degrees per second of change is occurring every second, right? Like the temperature acceleration, so to speak. If you notice that that is directly proportional to the temperature itself, but always in the opposite direction, i.e. with a negative sign, i.e. you notice that is equal to the temperature itself, but times some constant, and then times -1, then what you'll find is that temperature is oscillating harmonically in time, i.e. you'll find that if you plotted out the temperature on a coordinate axes, if you made a graph of temperature as a function of time, you'll get a cosine function. Like any system that is described by this second order differential equation, this particular one, any system for which the second time derivative is equal to a negative times a positive constant times the system variable itself, any system that does that is a harmonically oscillating system, i.e. the dependent variable that we're measuring is oscillating harmonically in time and therefore is describable by a cosine function. What cosine function? The cosine function, like remember, I'm using Z to mean any variable that we're looking at all, any measurable dependent variable. And whereas time, I'm fixing as the independent variable in my mind, then if Z is oscillating harmonically, then Z equals Z naught, like the initial value of Z, times a cosine of omega t. And what is omega? Like this is the whole purpose of this whole lecture is like, what is the deal with omega? Again, remember, I only introduced omega last class. When I introduced it, we didn't know much about it. We just knew that it was a placeholder. Omega, just up until this moment, stood for some number that had to be there inside the cosine function, basically just to ensure that units work out correctly, consistently, coherently, logically. So up until this moment, omega is just some number that's measured in radians per second. That's like all I know about it so far. In the case of the mass on the spring, it turns out that omega was equal to square root of k over m. But in general, what was k over m? K over m was the constant before the x on the right-hand side of d2x dt squared equals negative k over mx, right? Remember, like with a mass on a spring, the differential equation was d2x, like here, let me just write this to remind you. Okay, so like what I'm trying to do now is I'm trying to go from one physical particular circumstance, I'm trying to generalize it to a mathematical relation in general, right? So remember, we had d2x over dt squared equals negative k over mx. That's what we originally had, like that's Hooke's law for mass on a spring. What I'm saying now is, let's not get bogged down in x. Not every oscillator in the world is something that's literally moving back and forth in the x-axis, and not every oscillator in the world necessarily has a spring, like literally a metal coil with any kind of stiffness constant. So what we had was d2x dt squared equals negative k over mx. I'm saying in general, the format of that differential equation was d2 variable over dt squared equals negative constant times variable. That's what the form of that blue Hooke's law equation was. I'm saying now, what the K over M was just some constant. As long as there is a constant before the dependent variable, squeezed in between the dependent variable and the negative sign, as long as that's a constant, then we have a simple harmonic oscillator here. So what I'm saying is from now on, whatever that constant is, for any system that we ever encounter, any simple harmonic oscillator, any measurement Z, as long as d2z dt squared equals negative times some constant times Z, then it's a harmonic oscillator. So from now on, I'm going to call that constant omega squared. I'm going to call that I'm going to call it omega squared. In the case of a mass on a spring, it was K over M. In the case of a pendulum, it might be G over L. In the case of an electric temperature, it might be like root mean square speed over mass or something of molecules. What I know is, whatever that constant is, I could call it K over M. I could call it C for constant. I could call it Y for Yaverbaum, but I'm going to call it from now on omega squared because the thing that we just actually realized without realizing it 5 minutes ago is that the square root of whatever that thing is omega, the omega in the cosine term. In other words, the omega placeholder that we put in the cosine function, I still don't know quite what it means. But I know that it's got to be the square root of whatever the constant is in the differential equation, because I know when I differentiate the cosine function twice, that thing, omega, is going to come out twice from chain rule being operated twice. In other words, when I take one derivative, omega is going to come, I'm going to get like negative Z naught sine omega t all times omega. And then I'm going to take the derivative again. And because of chain rule again, the whole thing is going to be multiplied by omega again. So I'm going to get omega squared in front of the whole thing, no matter what. So whatever that omega is right there, it's going to be squared and end up as the constant in the differential equation. So put another way, whatever the constant of the differential equation is, the square root of that will be omega. Let me just see if I can say that one other different way. Let me just do one quick example of what yeah. Yeah. This will help a lot with the next homework that's coming anyway, for what it's worth. Let's just say that we knew that there was some variable Q. Like, I don't know what it is. I mean, it ultimately means charge, but it doesn't say there's some variable called Q that's a dependent variable. And we know that this differential equation applies to Q, like we got data from the lab or something like that. So we know that let's just say we know. Say we know that d2q over dt squared equals negative 25q. Like we just know that that differential equation is true. Then what I'm saying is that we necessarily know, then if that's true, then What I'm saying in as concrete terms as I possibly can say is I'm saying if you know that there's some variable that obeys that second order differential equation, if you know there is some dependent variable such that d2 it over dt squared equals negative times some constant times it itself, if you know that that differential equation applies to that variable, whether you can see metal springs, whether you can physically imagine what the variable is, whether it's temperature or something you've never heard of like electrical charge. Okay, cool. Thank you. Yes, thank you. Got it. Cool. Just get the video, please, or get the notes. Yeah. If you yes, thank you. If you just know from knowledge that that differential equation like applies to some dependent variable Q, then what you know is the value of Q is oscillating harmonically, like it's acting like the position for a mass on a spring. You'll know that the value of Q is going up, down, up, down, up, down, like a cosine, I mean, as a cosine, and you'll specifically know that the value of Q at any given moment in time will equal its initial value, whatever that is, times cosine of 5t. Now, where did I get the 5 from? The whole thing I'm trying to say right now, that's like, it's really easy once you get it, but it really seems out of nowhere until you get it. I'm saying that the thing, like I'm saying that the thing that will go before the t in the cosine will always, that thing that we're calling omega, that will always be the square root of whatever the constant was in the differential equation. That's what I'm saying. That if you have that differential equation, like we've now spent all this time solving this differential equation, we spent all this time because we solved it once and for all. We're never going to have to solve it again. We now know if we ever see that differential equation, the solution is a cosine of omega t. And what's omega? It's always going to be the square root of whatever that constant is in the differential equation, whether that constant is k over m or g over l or whatever, or just some number that we know. Okay, you'll get more and more practice with this, but that's why from now on we're going to call that constant in the differential equation omega squared, just because we're anticipating, we know in advance that it is the square of whatever omega is going to be in the cosine function. Okay, now, so again, this is like really weird until you get it. I recognize that. That's why I'm like screaming and yelling, and I'm going to say it a million times because every semester it's like, it's very backwards thinking. It's very reverse. And I don't mean backwards like it's messed up, but this is kind of like building a puzzle from the final answer to the puzzle or something like that. But once you get it, you'll see all I'm saying is whenever we want to know what omega is in the cosine function, it's going to be the square root of whatever constant term came before the variable in the differential equation, which okay, that's all I'm saying. Like if that were 36, then the number down here next to the cosine would be a 6. If that number was 16 up there next to the Q, then the number down here at the bottom of the page would be a 4. Like that's all I'm saying, really. But with 50, then you might say, well, then you still got 15 minutes left. What else are you going to say? Well, with 15 minutes left, what I really want to say that also might be part of why people still might be confused about this is, well, what the heck is this omega? Like I'm telling you now that omega is always the square root of whatever that constant is. But what the heck does it mean? What does it do for us? What's the deal with it? Good question. Glad you asked. Okay, so that's the rest of the period. So the question is, what really is omega? Like, what do I mean by this omega thing? Like, I'm sort of telling you in some ways how to get it, but I haven't told you yet how to interpret it or what it's doing for us. So the question is, like, what does it really mean in the context of cosine? Okay. Well, what we know so far about omega, it's a constant. It's a constant. It's a number that doesn't change for a given oscillator. We know that it's measured in radians per second. Radians per second, something per second. So it's a rate. It's some kind of rate in time. Now, it's not a speed. It's not meters per second. It's not how far something's going in time. It's radians per second. What the heck is a radian? Good question. I have to get to that. I'm not assuming that we're all comfortable with radians. We need to be by the end of the class, but what I could say for the moment is this is some sort of rate. It's not a rate of motion. It's a rate of cycling. What we're talking about here are oscillators, harmonic oscillators. we're talking about systems. And this is really, again, the purpose of all those questions, questions 1 through 4, 5, 6, 7, 8. They were all trying to build up the idea that that a simple harmonic oscillator, a mass going back and forth on the spring, is on the one hand doing something very simple. On one hand, it's doing something very, very patterned, very predictable, very constant. I mean, it's going back and forth forever. And it's going in this pattern, like maximum potential energy, minimum kinetic energy, to maximum kinetic energy, minimum potential energy, to maximum potential energy, minimum kinetic, back and forth and back and forth. Also, all of its rates of motion, its position, its velocity, its acceleration, even its jerk. It's what all these things are doing something very, very patterned, very predictable, but none of them is constant, right? Like on the one hand, a mass on a spring or an oscillator is very simple on the one hand, but it's not very easy to sink our traditional physics teeth into, because, like, for example, the position is always changing. And second of all, the velocity is continuously changing, right? It's never got the same velocity 2 moments in a row. It's never even got it's never got the same acceleration 2 moments in a row. And as we found out in questions 7 and 8 last week, it doesn't have the same acceleration of acceleration. Like, it doesn't have the same jerk 2 moments in a row. It doesn't have the same fourth derivative of position. Like, all the derivatives are doing something very patterned and very reliable, but all very different. So if we wanted to use our traditional ways of talking about motion, like velocity, or if we wanted to use kinematics, if we wanted to use velocity, acceleration, none of those things really are holding steady at all for an oscillator. Yet something is holding steady. There's got to be something predictable about it and patterned, some way of capturing all of these patterns that are all happening at once. What's holding steady about an oscillator is its oscillation, is the fact that it's cycling back and forth. It's making round trips over and over and over again, or round trips over and over and over again, or round trips over and over and over again. And it's doing that at a regular rate. The regular rate at which it's cycling is ultimately captured by omega. Omega is a measurement of radians per second. What is a radian? I'm going to tell you right now. Well, I'm going to tell you more ways than one. A radian, and I know no one usually comes to this class liking radians. I have no illusions that you love radians at the moment. At this point in my life, I love radians. Some of my best friends are radians. I love radians, but I didn't at first. But once I understood them, I did. So let's back up. If we're going to talk about radians, let's talk for a moment. Radians are a way of measuring angle. What is an angle? You might think an angle is something like this. That you might think an angle is something like that. That's what I thought for the longest time. Now, I'm not saying that's wrong. I mean, that is an angle, but that's a very unhelpful way to think about an angle. It's what gets us into trouble. What an angle is a portion of a circle. Wait, hold on. In fact, let's have a picture. Oh, sorry. Okay, we've got 9 minutes. I'm aware. And honestly, this, please, even if I've like try to tune in for this, because again, I'm assuming that most people are not that thrilled about radians. You might sort of get them, but you don't love them. You prefer to use degrees. Like, I get that, but I'm here to try to convert you. Like, and by the way, I have to, because degrees really will not work for the rest of this class. I'm totally sympathetic if you prefer degrees, but please join me in attempting, like, clear your mind, open your mind to the possibility that if you really could get radians, you might ultimately like to work with them more, and you have no choice. So here, not yet. No, it's not. A good question. It will be on Wednesday. But it's not due Wednesday, but it will be. But good question. And now bear with. Sorry, someone's in the direct chat. Someone's very legitimately asking, "Is the second homework post yet?" And no, it's not. Like, I will, but now I'm going to ask everybody to bear with me. I've got 8 minutes. This is a really important concept that, in theory, you might think was taught to you years ago, but my experience is that it never does sink in years ago. So let's try it now. What I'm saying here is this. First of all, like, a radian is a way of measuring angles, okay? Just like degrees are ways of measuring angles. But what is an angle? An angle is a fraction of a circle. That's what an angle is. If you think about it, what's a 360? Like, everybody knows 360, like, people think they know degrees, right? So what's a 360? It's a full circle, right? What's a 180? It's a half circle. What's a 90-degree angle? Everybody can recognize a 90-degree angle. What they're recognizing is that it's a fourth of a circle, if you think about it. And when I say it's a fourth of a circle, right? When I say an angle, a certain angle, and I don't care whether you call it a 90-degree angle, or you call it a right angle, or you call it a pi over 2 radian angles, like, we'll get to that in a minute, but it doesn't matter what you call it. The fact is, people, when they recognize angles, when you really think about it, what you're recognizing is a certain fraction of a circle, and you're recognizing it regardless of how big the circle is. Like a 360 is a 360, whether you go all around the earth or you just twirl around your own body. Like, literally, my 7-year-old younger son that you've all met a million times, who plays Pokemon, whatever, he totally knows what a 360 is. He's always talking about, "Oh, look, Dad, I just did a 360. Right? What is he saying? He's saying he just did a full circle. And he knows that a 180 is a half circle. Okay, so forget degrees or radians for a moment. Just recognize, first of all, that what angles are portions of circles. Now, when we say mathematically that in theory, that really theta, and look at the bottom right in the blue, right? Theta triple equals sine S over R. That means angle theta, like the definition of an angle measured in whatever units, is equal to arc length over radius. Let me write that again up at the top, right? That's a way of saying, if you think about it, when we say this, and this, I never understood this until I understood it, like, if you know what I mean. When we say that an angle is an arc length divided by a radius, we're just saying, well, like, what's arc length? It's how much of the circle you went around. Angle is how much of the circle you went in meters. Angle would be like, did I go 12 meters or did I go all the way around 24 meters or whatever, but then divided by the radius, so that we're saying, look, we don't want to care about, like, sure, you could go 300 if you had a circle whose radius was 1 meter, then to go around the whole circle, you'd go 360 meters or whatever, not literally, but then if it was a bigger circle, you would carve out a much bigger arc length, and we don't want to get bogged down in that. So we're saying whatever your arc length is measured in meters, now just divide by the radius in meters. We're saying, let's just all imagine that we're saying per every unit of length in the radius of that circle, how much arc length did you do? We're just saying, in other words, what an angle is a fraction of a circle that doesn't depend on how big the circle is. A 90-degree angle is a 90-degree angle, whether it's cut from a small circle or a big circle. Specifically now, I'm saying an angle is arc length measured in meters divided by radius measured in meters. So the meters cancel out, and an angle truly itself is dimensionless. It doesn't have any units. Like, it doesn't, degrees are made up, radians are made up. An angle itself is just a pure ratio. It's just a fraction of a circle. But then we say, and I know I have 4 minutes. I'm saying that every circle in the world, no matter how big it is, has a circumference that is 2 pi times its radius, right? Or in other words, pi times its diameter. Pi is just this universal relationship that is just the ratio of how far around a circle you go versus how far you go across the circle. Right, so the circumference, as you all know, the circumference of any circle is 2 pi times the radius of that circle. And pi is just a number. It's a little bit more than 3. It's less than 4, but it's just a number. It's a weird number, but it's just a number. It's a constant number, right? So I'm saying this. Going around a whole circle, you could call that 360 degrees. You could say that a degree is a portion of a circle that's 1/360th of a circle. You can do that if you want, and you're used to it, so you do. But, or you could just as easily say that to go around an entire circle, or you could divide the circle into radians and say there's exactly 2 pi radians in an entire circle. In other words, 2 pi radians equals 360 degrees. And then you could say, well, what's a radian? Just that. A radian is approximately a 1/6 of a circle. If a degree is approximately a 360th of a circle, then a radian is what you get if you divide the circle into approximately 6 parts. Where did I get 6 from? 6 is 2 times pi, approximately. It's not exactly, but approximately. If you just divide, from now on, if you just divide a circle into approximately 6 parts, each part would be a little bit less than 60 degrees, okay? Each one of those parts, each 1/6 of a circle is what we call a radian. Okay, a radian is a 1/6 of a circle. What does that have to do with oscillations and cosines and all this? Is that therefore a radian is a 1/6 of a cycle. I'm saying this, and this is just, I'm saying this. You can start copying that while I'm talking. I know I have 1 minute. I'm saying if you think of the easiest thing to measure or observe in the lab, how much time it takes to do a full, what I'm saying is we're going to take all the math that we already know about circles and graft it onto all of the math that we need. We're going to take all the math that we already know of circles and graft it onto the situation we have here with cycles. We're just going to say, oh, there's 2 pi radians per every circle. Oh, so there's 2 pi radians to every cycle. And just bear with, if you have to go right now, please go. But I'm just going to take like a minute and a half more just to wrap this up, and then I'm done. If you can just bear with me for like a minute and a half, I appreciate it, and then we're done. But if you have to go, then go. But I'm saying this. We're talking about cyclical motion here. We're talking about oscillation. The speed's not constant. The acceleration's not constant. Nothing is constant except for the rate at which these things cycle. The easiest thing to measure would be the amount of time it takes to do one cycle, one there, back, round trip. Call that the period, capital T. That's what it says here. T is a period of time for one cycle, there and back. It's measured in seconds per cycle. You can flip that. Now, that's the easiest thing to relate to and measure in the lab. You can flip that. Okay, yes, have a good night. Sorry that I'm just about done to anybody who can hang for like 1 more minute, but if you have to, but obviously I'll post this video and I'll post the notes, blah, blah, blah. But period is the amount of time for one round trip cycle. Standard frequency is the inverse of that, the reciprocal of that. It's cycles per second. If it takes you 4 seconds to do a cycle, then you're doing 1/4 of a cycle per second. We call one cycle per second a hertz. In order to deal with the math of all of this, to use math that already exists, to not have to reinvent the wheel, to be able to use cosines and all that stuff, we just make one more conversion. We say, oh, since in each cycle there's 2 pi radians, which is what I'm saying. I'm saying a cycle is 2 pi radians, or put another way, what's a radian? Essentially a 1/6 of a cycle. We can measure things in omega, in angular frequency, in radians per cycle. That's just like measuring, if you measure something's oscillation rate in radians per second, you're just measuring its cycling rate in cycle 1/6 per second. In other words, whatever the standard frequency, and this is my last thing, this is the last page, whatever the standard frequency of some oscillator is, if it's doing 3 cycles per second, then we can say that its omega is 6 pi radians per second, because in each cycle, there's 2 pi radians. It's just a conversion factor. We're saying that in every cycle, there's 2 pi radians. We're saying that every radian is just a sixth of a cycle, approximately. So omega equals 2 pi times f, or in other words, omega equals 2 pi over t, capital T, where capital T is the period. That's it. Sorry to keep you, but that's it. Thank you guys for waiting so much. And I'll post the next homework on Wednesday, but have a great, thank you. Thank you. And thank you for hanging out. Sorry about that. And I'll see you Wednesday. Thank you for being patient. Thank you. And I totally noticed who stayed. Thank you. All the people that compete about who gets here first, they don't actually stay till the end, do they? But you guys do. Oh, did I say that? Oh, sorry. We're still. No, thank you, Lizzie. Thank you, May. Thank you, Elizabeth. Thank you, Noel. Totally noticed. Totally appreciated. You could put that in for participation. I stayed late. You can do that. But okay. But thank you guys. Okay, I'm stopping the recording.